What scientific phenomenon do you wish someone would explain better? I've been studying viruses lately, and have found that the line between virus/exosome/self is much more blurry than I realized. But, given the niche interest in the subject, most articles are not written with an overview in mind. What sorts of topics make you feel this way? Quantum computers. Not like I'm 5, but like I'm a software engineer who has a pretty decent understanding of how a classical Turing machine works. I can't tell you how many times I've heard someone say qubits are like bits, except they don't have to be just 1 or 0 without providing any coherent explanation of how that's useful. I've also heard that they can try every possible solution to a problem. What I don't understand is how a programmer is supposed to determine the correct solution when their computer is out in some crazy multiverse. I guess what I want is some pseudo code for quantum software. I recommend Computer Files videos had the same problem as you. What finally made me feel I sort of cracked it was those videos. The way I think of it now is, they let you do matrix multiplication. The internal state of the computer is the matrix, and the input is a vector, where each element is represented by a qubit. The elements can have any value 0 to 1, but in the output vector of the multiplication, they are collapsed into 0 or 1. You then run it many times to get statistical data on the output to be able to pinpoint the output values more closely. I think there's no way to understand quantum computing without first understanding some linear algebra, specifically tensor products. How 10 two-dimensional spaces give rise to a 1024-dimensional space, how the Kronecker product of 3 2x2 matrices is an 8x8 matrix, and so on. If you're comfortable with that, here's a simple and precise explanation of quantum computing: 1. The state of an n-qubit system is a 2 to the power of n-dimensional vector of length 1. You can assume that all coordinates are real numbers, because going to complex numbers doesn't give more computational power. 2. You can initialize the vector by taking an n-bit string, interpreting it as a number k, and setting the kth coordinate of the vector to 1 and the rest to 0. 3. You cannot read from the vector, but exactly once, destroying the vector in the process, you can use it to obtain an n-bit string. For all k, the probability of getting a string that encodes k is the square of the kth coordinate of the vector. Since the vector has length 1, all probabilities sum to 1. 4. Between the write and the read, you can apply certain orthogonal matrices to the vector. Namely, if we interpret the 2 to the power of n-dimensional space as a tensor product of n two-dimensional spaces, then we'll count as an O1 operation any orthogonal matrix that acts non-trivially on only O1 of those spaces, and identity on the rest. This is analogous to classical operations that act non-trivially on only a few bits, and identity on the rest. The computational power comes from the huge size of matrices described in 4. For example, if a matrix acts non-trivially on one space in the tensor product and as identity on 9 others, then mathematically it's a 1024 by 1024 matrix consisting of 512 identical 2x2 blocks, but physically it's a simple device, acting on one qubit in constant time and not even touching the other 9. Very simplified explanation. If you understand Turing machines, you probably also understand other automata. So you probably understand non-deterministic automata. 1. A quantum computer is like a very restricted non-deterministic automaton, except that the do several things at once is implemented in physics. That means just like a NFA can be exponential faster than a DFA, a QC can be exponential faster than a normal computer. But the restriction on QCs makes that a lot harder to do, and so far it only works for some algorithms. As to why quantum physics allows some kind of non-determinism, if you look at particles as waves, instead of a single location you get a probability function that tells you where the particle is. So a particule can be in several places at once. In the same way a qubit can have several states at once. Greater than what I don't understand is how a programmer is supposed to determine the correct solution when their computer is out in some crazy multiverse. Because one way to explain quantum physics is to say that the waveform can collapse, too, and produce a single result, at least as far as the observers are concerned. There are other interpretations of this effect, and this effect is what makes quantum physics counterintuitive and hard to understand. 1. 2. Here is a video of a researcher at Microsoft Quantum lecturing on this, quantum computing for computer scientists. However, even with understanding how a quantum computer works at its most basic level, I still have difficulty understanding the more useful quantum algorithms. I honestly recommend the following. 1. Pick up the standard textbook, by Nielsen and Chuang, Quantum Computation and Quantum Information. Read the first 2 to 3 chapters. 2. Solve the exercises for the Q-hash programming language. I found quantum computing without the physics epically helpful. Explains in terms a computer scientist can understand. As in, it sets out a computational model and explores it, regardless whether we can physically realize that machine. Hope this helps. IBM's Quantum Experience is great for this. It walks you through the quantum gates you can use and lets you write small programs for quantum processors. I found that to be the clearest way of understanding what QCs do. Pseudocode for quantum computers is currently linear algebra. Fortunately, most programmers have the required linear algebra to get a thorough understanding of the basics. Check this out, fair warning, I did have to brush up on my linear algebra a bit, but it's worth it emo. Friends in the know say that when you understand this article, you understand quantum computers. I had an aha moment with quantum computers a few months ago when reading an article that explained it as probability distributions. I don't think I have the complete understanding in my mind anymore, and I wish I had saved the article, but looking into how quantum computers essentially serve as probability distribution crunching machines might help with your understanding. You're in luck, my friend. Perl has had a quantum computing module since the late 90s. As far as I can tell, this one still outperforms all existing hardware implementations. Nobody understands quantum mechanics. Lots of people know how to apply it. I don't think quantum technology is going to go anywhere until physicists revamp the theory and the pedagogy in a way that makes it comprehensible. I say this as someone who passed 2 semesters of graduate QM. This podcast episode has an amazing explanation by one of the top researchers in the field. Basic idea is that by making the amplitudes of the qubits destructively interfere with each other in certain ways, you can eliminate all of the wrong answers to the question you're trying to answer. Not quantum computers per se, but I had my aha moment when I saw quantum computing as linear algebra, with probability coefficients. It's mostly working on superpositioned qubits while doing the calculation and then making them, with linear transformations, as likely as possible to collapse on the solution, when measured. I looked briefly at QCs and I understood them as kind of a machine that doesn't try every possible solution. It is in every possible solution, and then you can somehow lock it in the state that is the solution to your problem. Kind of like NP problems are hard to find a solution but easy to verify a solution. I think because it has less applications for traditional software and more applications for efficiency of embedded systems. But it could have some bleeding edge new applications from the TCP/IP space for urgent point, new methods for cryptography, or speeding up algorithms for searching. Macron ___/ Macron. Qubit is physical random generator, which quickly oscillates between 0 and 1. It does that so quickly, so scientists must operate with probabilities to perform calculations. They create analog, quantum computers, where right solutions are much more probable than wrong ones, then let system to figure them out, then sample solutions periodically. Short answer, there isn't an easy answer. Yet. Give QC another 50 years. Proof. Just look at all the replies you got, each one is dozens of pages of complex, imaginary, math, control theory, and statistics. The hardest part of QC is exactly what you described, how to extract the answer. There is no algorithm, per se. You build the system to solve the problem. This is why QC is not a general-purpose strategy. A quantum computer won't run Ubuntu, but it will be one superfast prime factoring coprocessor, for example, or Pathfinder, or Root Solver. You literally have to build an entire machine to solve just one problem, like factoring. Look at Shor's algorithm. It has a classical algorithm and then a QC coprocessor part. Think of that like an FPU looking up a transcendental from a ROM. It appears the FPU is computing sign, but it is not, it is doing a lookup. Just an analogy. The entire QC side is custom built just to do this one task. In this example he factors 15 into 5 by 3, and the QC part requires FFDs and tensor math. Oi! Like I said, it will take decades for this to become easier to explain. For fun, look at the gates we're dealing with, like square root of naught. In short, I'd say you need to understand the underlying mathematics to intuitively understand the operations that underpin the algorithms. And since this is quantum mechanics, there's no real ELI 5 version that can give you any useful understanding. Macroeconomics. Central banks are creating a trillion here, a trillion there, like nobody's business. But what are the consequences? What is the thought process that central bankers have gone through to make these decisions? Also, why, exactly, are they buying the exact assets that they are buying, government debt, high-yield bonds, etc., and why not others, for example stocks, or put money into startups? And then, what happens if a debtor pays back its debt? Is that money consequently getting erased again, just like it's been created? What happens if a debtor defaults on its debt? Does that money then just stay in the economy, impossible to drain out? What is the general expectation of the central banks? What percentage of the debt is expected to default and how much is expected to be paid back? And specifically in the case of central banks buying government debt, are central banks considered easier creditors than the public? What would happen if a country defaults on a loan given by a central bank? Would the central bank then go ahead and seize and liquidate assets of the country under a bankruptcy procedure to pay off the debt, like it would be standard procedure for individuals and companies? The consequences are supposed to be inflation. Instead, we seem to only get asset inflation, houses, stocks, and not consumer goods inflation, flour. From a former econ professor who I spoke to recently, the central bankers aren't thinking about inequality or inflation right now, they're just trying to avoid the apocalypse. The liquidity injected is supposed to be taken out later, thus removing the inflationary distortion. Whether it will or not is anyone's guess. 2008's injections have yet to be taken out. Central banks are easier creditors because, while autonomous, they are the same country as the government. So it's technically like owing yourself money. A central bank that cooperates with the debtor country, itself, would never force a default, and is thus never an acute problem. Of course, infinite money printing should lead to dangerous inflation. I have done plenty of serious reading on economics, but as far as an approachable start, I don't think we can do better than this. You or a friend wants a crash course on econ, check it out. One approach is reductio ad absurdum. If central banks can create money without negative effects, then why tax people? Why even work? Can't we just print enough money for everyone and live happily ever after? I realize these questions are quite provocative and their answering only explains if it will work but not how or when it will fail. America Incorporated, which dated by I believe Mary Meeker, has one view showing USA on a gap basis. It's not pretty. Leverage is too high. Profit margins are negative. Growth, in this case government receipts, underperforms entitlement spend. Interest is some non-material portion of revenue such as 15% to 20%, caveat, even the most highly leveraged private equity-bought companies don't spend more than 25% of revenue of amortization and interest, generally speaking. A better but harder resource is I believe by Piketty, the inequality guy. From balance sheet recessions there's usually only a few ways out. He and his co-authors go through every single KNKWN recession in every single country, obviously biased towards recent and Western. What I took away from it is that without population growth the US needs hyperinflation, to default on its debt, or to increase tax revenues sharply and/or decrease entitlements sharply. It's up to you to guess which one of those three is most likely. But the budgetary situation is not tenable. Consequences of creating a trillion. Economic policy is largely driven by political necessity. During the Great Depression, FDR's policy was based on Keynesian economics. Keynes aside, FDR tried everything to alleviate the suffering of the people, because the danger was not in implementing the wrong policy, instead the danger was in doing nothing. Later, the Austrian school of monetary theory was popular where it prescribed increasing the money supply to pump up a troubled economy. During the last financial crisis, Obama's administration prescribed quantitative easing where the government bought the junk to keep the big banks solvent. The big banks were too big to fail and had to be rescued. The consensus of the last 10 years is that quantitative easing restored the financial health of the elite and the corporations, but the middle class is still left behind, assets that they are buy. The idea is to keep the banking system solvent and to prevent a domino effect where the liquidation of one big bank will result in a run on other banks. The big banks got into trouble because they took depositors' money and invested in junk which went belly up. The federal government insures everyone's bank deposits. If the banks went bellied up, the FDIC would have to pay out. Better that the banks stay solvent. There are cases like Greece defaulting on its international loans. The EU forced Greece to agree to an austerity plan lowering Greece's payments if Greece changed its national spending, which is deeply unpopular in EU and Greece. But there is no other alternative. Well, the alternative is what happened to Weimar Germany after World War I, hyperinflation, economic destruction, and the longing for a savior. You cannot really create money, but they do it anyway because the natural pricing mechanisms, laws of supply and demand, take a non-null time to reach a new equilibrium. So the aim is to take advantage of this transient fluctuation and the way the ripple propagates. But even if in a perfect, or future, world, everybody reprices instantly all the goods relatively to the new amount of available currency, there is still an effect, which is how is distributed the newly created currency, who get the new shiny coins. So this is equivalent, if the repricing is done, to a kind of global instantaneous tax and subsidies. They tax everybody by the percentage of currency created, relative to the total existing amount, and the lucky ones receiving the fresh money are getting thus a subsidy. I've wondered the same thing lately whenever someone here posits that defaults cause the destruction of money. I'd love to see this properly explained, because it definitely has a counterintuitive ring to me. PhD student here. Not expert on all those questions, but greater than macroeconomics. Central banks are creating a trillion here, a trillion there, like nobody's business. What is the thought process that central bankers have gone through to make these decisions? The general consensus is that central banks should stay passive and keep prices stable. However, in periods of crisis, like the one we live in, the central bank could support economy. In ordinary times, creating trillions would lead to inflation. But here the idea is more to save the economy in the short term because it's always cheaper than repairing it. Central bankers agreed to create trillions, such that banks do not go bankrupt like they did in 1929. By creating trillions, they also keep interest rates low for government such that they can still borrow. Greater than, but what are the consequences? Some inflation. Another consequence is that investors will invest in riskier assets afterward to keep their profitability target. Again, because lending trillions will lower the interest rates. Greater than also, why, exactly, are they buying the exact assets that they are buying? Government debt, high-yield bonds, etc. They usually buy low-risk, highly liquid assets. Putting trillions in startups is infinitely complicated for a central bank because it implies high monitoring costs, and it also takes a lot of time to create those kind of contracts. Remind that the goal is to provide lot of liquidity to the economy as fast as possible. There is also an academic debate about giving money directly to the general public, known as helicopter money, but with little attention from central bankers. Greater than, and then, what happens if a debtor pays back its debt? Is that money consequently getting erased again? Yep, pretty much. Apart from fiat money, money is constantly created and destroyed. It is mostly created by private banks when they grant loans. And it is destroyed when you repay it. Of course they cannot do whatever they like and create at will, but remember that deposits do not make the credits, but in some way it defines how much you could create. Greater than, what percentage of the debt is expected to default and how much is expected to be paid back? What would happen if a country defaults on a loan given by a central bank? Central banks buy bonds, and bonds are pretty much always paid back. And if not, the central bank will not suffer much. Cases of countries not reimbursing are very scarce and exceptional. I can just think of Argentina. Anyway, a country cannot go bankrupt like a person. And in general, comparing countries with individuals or companies is not a good idea. Countries are here pretty much forever. In a financial sense, you don't. Countries can waive taxes, individuals cannot. My thoughts on this modern monetary theory is that central banks are just creating these trillions, but they are doing it at a relative rate to each other. I think eventually it will have bigger consequences, but it will take some time for these trillions to filter on down. I remember once outcome of the 2008 crisis was that consumer goods like cereal boxes stayed the same size, but the bag inside the box got smaller. Not sure I'd class it as a science, but here's my take. Though I'm no expert, and certainly agree this stuff could be better explained. Macroeconomics. Central banks are creating a trillion here, a trillion there, like nobody's business. But what are the consequences? Nobody quite knows. It's still hotly contested between left-wing lovers of Keynes and right-wing believers in austerity. Greater than, what is the thought process that central bankers have gone through to make these decisions? Probably largely a political one. Central banks may be trying to fulfill a remit set by law, for example Bank of England, keep inflation below X%, and are trying to deliver on that. Why? Too much or too little inflation both cause problems. I guess we somehow reached consensus on a sane amount that keeps pace with genuine growth of wealth within the economy. Greater than, also, why, exactly, are they buying the exact assets that they are buying? Government debt, high-yield bonds, etc., and why not others, for example stocks, or put money into startups? I think this is about distributed decision-making. The central bank does not have the expertise to decide which stocks or startups represent the best investments. The examples here involve lending money to government, presumably the idea being the latter is better placed to decide what to do with the money. Another example is buying assets from other banks, which are again better placed to decide which businesses/homeowners/ etc. represent a more sound investment as they do it on a daily basis. From a profit/loss point of view, of course we debate whether or not that's the case on a societal level. Greater than, what would happen if a country defaults on a loan given by a central bank? Internally it would depend on laws/balance of political power within the country. Between countries, depending on the currency, the country could do crazy stuff like print excessive amounts of money to repay the loan. Germany did this in the 1930s, leading to hyperinflation, or they could, just as you say, default. The country's credit rating would then be downgraded, making it harder for them to raise credit in future. Greater than would the central bank then go ahead and seize and liquidate assets of the country under a bankruptcy procedure to pay off the debt, like it would be standard procedure for individuals and companies. Not the bank, but the country making the loan, may first negotiate some debt relief with strings attached, for example preferential trade agreements. Beyond that, I have no idea what precedent exists. I would like to understand how cellular biology processes actually work. Like, how do all the right modules and proteins line up in the right orientation every time? Every time I watch animations, it seems like the proteins and such just magically appear when needed and disappear when not needed. 0. Sometimes it's an ultra-complex looking protein and it just magically flies over to the DNA, attaches to the correct spot, does its thing, detaches and flies away. Yeah, right? As if the protein is being flown by a pilot. How does it really work? 0? They don't. This is a pet peeve of mine, and it's reinforced by animation after animation. Everything is being jostled around randomly. The molecules don't have brains or seeker warheads. They can't decide to home in on a target. The only mechanisms for guidance are diffusion due to concentration gradients, movement of charged molecules due to electric fields, and molecules actually grabbing other molecules. It's all probabilities. This confirmation makes it more likely that this thing will stick to this other thing. You may have heard that genes can be turned on or off. How? DNA is literally wound on molecular spools in your cell nuclei. When the DNA is loosely wound, other molecules can bump into it and transcribe it, the gene is on. When the DNA is tightly spooled, other molecules can't get in there and the gene is off for transcription. There's no binary switch, just likelihoods. Everything is probabilistic, but the probabilities have been tuned by evolution through natural selection to deliver a system that works well enough. It's not so much magic as it is the sheer rate of molecular collisions in the cytosol. There are so many collisions happening that at least one of them will do what you want. Here's a back of the napkin example, admittedly with many simplifications. A TRNA molecule at body temperature travels at roughly 10 meters per second. Assuming a point-sized TRNA and stationary ribosome of radius 125 times 10 to the power of minus 10 m, the ray casted by the moving TRNA will collide with the ribosome when their centers are within 125 times 10 to the power of minus 10 m of each other. The path of the TRNA sweeps a collidable circle of the radius of 125 times 10 to the power of minus 10 m, for a cross-sectional area of 5 times 10 to the power of minus 16 square meter. Multiplied by the TRNA velocity, the TRNA sweeps a volume of 5 times 10 to the power of minus 15 cubic meter per second. Constrained inside an ordinary animal cell of volume 10 to the power of minus 15 cubic meter, the TRNA would have swept the entire volume of the cell 5 times over in a single second. Obviously, the collision path would have significant self-overlap, but at this rate it's quite likely for the two to collide at least once any given second. Now, consider that this analysis was only for a single ribosome/TRNA pair. A single ribosome will experience this collision rate multiplied by the total number of TRNA in the cell, on the order of thousands to millions. If a ribosome is bombarded by tens of thousands of TRNA in a single second, it's very likely one of those TRNA will, 1. Be charged with an amino acid, 2. Be the correct TRNA for the current 3-nucleotide sequence, and 3. Collide specifically with the binding site on the ribosome in the correct orientation. In actuality, a ribosome synthesizes a protein at a rate of 10 amino acid residues per second. Any given molecule in the cell will experience millions to billions of collisions per second. The fact that molecules move so Fast relative to their size is what allows these reactions to happen on reasonable timescales. The issue with these animations is that they're getting rid of all the thermal noise. In reality, single proteins are flying around the whole length of the cell many times a second, just from their thermal motion. And when processes like DNA transcription happen, they're not like a regular conveyor belt. A fraction of the time the machine will even accidentally run steps in reverse. However, if any of this were shown, the animations would become impossible to understand. Anytime something magically lines up, it means that those molecules randomly float around until the right ones bump into each other. Once they are in close enough proximity to bump into each other, intermolecular forces can come into play to get the docking process done. For something like transcription, once they are docked, think of it like a molecular machine. The process by which the polymerase moves down the strands is non-random. There are also several ways to move things around in a more coordinated fashion. Often you have gradients of ion concentration, and molecules that want to move a certain direction within that gradient. You also have microtubules and molecular machinery that moves along them to ferry things to where they need to be. You can also just ensure a high concentration of some molecule in a specific place by building it there. A friend of mine showed me this right up when I asked a similar question, and it helps to clear up a lot of the magic movement. But in a nutshell, the animations are heavily idealized, showing the process when it succeeds, slowing it way down, and totally ignoring 90% of the other nearby material so you can see what's going on. Then you remember that you have just a bajillion of cells within you, all containing this incredibly complex machinery, and it's really kind of humbling just how little we actually know about any of it. Not to discredit the biologists and scientists for whom this is their life's work, we've made incredible amounts of progress over the last century. It's just we're peeking at molecular machinery that is so very small, and moves so quickly that it's nigh impossible to observe in real time. A few different things help everything work. 1. Compartmentalizing of biological functions. It's why a cell is a fundamental unit of life, and why organelles enable more complex life. Things are physically in closer proximity and in higher concentrations where needed. 2. Multi-enzyme complexes. Multiple reactions in a pathway have their catalysts physically collocated to allow efficient passing of intermediate compounds from one step to the next. 3. Random chance. Stuff jiggles around and bumps into other stuff. Up until a point, higher temperature mean more bumping around, meaning these reactions happen faster, and the more opportunities you can have for these components fly together in the right orientation, the more life, stuff can happen more quickly. There's a reason the bread dough that apparently everyone is making now will rise faster after yeast is added if the dough is left at room temp versus allowed to do a cold rinse in the fridge. There are just less opportunities for things to fly together the right way at a lower temperature. 3a, for the ultra-complex protein binding to the DNA, how those often work in reality, is that they bind sort of randomly and scan along the DNA for a bit until they find what they're looking or fall off. Other proteins sometimes interact with other proteins that are bound to the DNA first, which act as recruiters telling the protein where to land. I studied bioinformatics and found the standard textbook, Albert's Molecular Biology of the Cell, 0, to be one of the most captivating books I've read. It's like those extremely detailed owner's manuals for early computers, except for cells. The amount of complexity is just absolutely insane. My favorite example, DNA is read in triplets. So, for example, CAG adds 1 glutamine to the protein it's building 1. There are bacteria that have optimized their DNA in such a way that you can start at a 1-letter offset, and it encodes a second, completely different, but still functional protein. I found the single cell to be the most interesting subject. But of course it's a wild ride from top to bottom. The distance from brain to leg is too long, for example, to accurately control motion from central command. That's why you have rhythm generators in your spine that are modulated from up, high, and also by feedback. Every human sensory organ activates logarithmically. Your eye works with sunlight, 500 million photons per second, but can detect a single photon. If you manage to build a light sensor with those specs, you'll get a Nobel Prize and probably half of Apple. 0. 1. Cells are tiny and the speed of sound is how fast air molecules move. Proteins are also not bouncing around as fast, but it's very still quick relative to their size. Next, often there are multiple copies of each component. That's half the story. Larger cells also have various means to clump things together to improve the odds. Speed of sound is 343 meters per second. Diameter of a cell nucleus is 0.000006 meters to give an idea. From a physics perspective, I bet you have two things happening. 1. These molecules are moving around a lot. The kinetic energy of molecules at room or body temperature gives them impressive velocity relative to their scale, and they're also rotating all together and internally. 2. Compatible molecules are like magnetic keys and locks. They attract each other and the forces align with meeting points. The same way that proteins fold spontaneously. So the remaining part is getting concentrations appropriate for what you want to happen, and that's a matter of signaling molecules and automatic cell responses to changes in equilibrium. It's a really chaotic system, and it's a wonder it works at all. I imagine that's also one reason life is imprecise, i.e. no two individuals are alike even with identical genes. There's a lot of extra entropy introduced by that mess of a soup. There are some animations that show how fast molecules and proteins go around in a cell. It's basically a bunch of extremely fast collisions and interactions going at random, that end up falling into proper configurations. The way science is taught in molecular biology, as in, visually, with proteins binding to receptors just like if it were fate, is usually completely wrong. I find most explanations of the equivalence principle that lies at the foundation of general relativity to be very lax. To wit, the idea is that you cannot distinguish whether you are in an accelerated frame or in a gravitational field. Alternatively stated, if you're floating around in an elevator, you don't know whether you're free-falling to your doom or in deep sidereal space far from any gravitational source, though of course, since you're in an elevator car and apparently free-falling. I think we'd all agree on what's most likely, but I digress. Anyway, what irks me that this is most definitely not true at the thought experiment level of theoretical thinking. If you had two baseballs with you in that free-falling lift, you could suspend them in front of you. If you were in deep space, they'd stay equidistant. If you were free-falling down a shaft, you'd see them move closer because of tidal effects dictated by the fact that they're each falling towards the Earth's center of gravity, and therefore at, very slightly, different angles. Of course, they'd be moving slightly toward each other in both cases, because they attract gravitationally, but the tidal effect presence is additional and present in only one scenario, allowing one to, theoretically, distinguish, apparently violating the bedrock equivalence principle. I never see this point raised anywhere, and I find it quite distressing, because I'm sure there's a very simple explanation and that general relativity is sound under such trivial constructions, but I haven't been able to find a decent explanation. You're right that this is glossed over in popular explanations, but the point you make is exactly the starting point for all formal courses and textbooks. The first part of the argument is that for single-point particles falling, the effect of gravity is the same for all particles. This suggests that we should model gravity as something intrinsic to spacetime itself, rather than as a field living on top of spacetime, which could couple to different particles with different strengths. The second part of the argument, which is what you point out, is that gravity can have non-trivial tidal effects. This had better be true, because if all gravitational effects were just equivalent to a trivial uniform acceleration, then it would be so boring that we wouldn't need a theory of gravity at all. This suggests that whatever property of spacetime we use to model gravity, it should reduce in the Newtonian limit to something that looks like a tidal effect, i.e. a gradient of the Newtonian gravitational field. That leads directly to the idea of describing gravity as the curvature of spacetime. So both parts of the argument give important information, both historically and pedagogically. Both parts are typically presented in good courses, but only the first half makes it to the popular explanations, probably out of simplification. The elevator car is a thought experiment that draws attention to the equivalence in sensation of acceleration on one hand, and being in a uniform gravitational field on the other hand. As you correctly point out, this particular thought experiment breaks down when you consider that all of the gravitational fields that we are accustomed to are non-uniform, and have apparent tidal forces. The real principle of relativity is a bit more subtle, sometimes called the strong principle, that the effects of gravity can be explained entirely at the level of local geometry, without any need for non-local interaction from the distant body that is generating the gravitational field. To describe the geometry of non-uniform fields, we need more sophisticated mathematical machinery than what is implied by the elevator car thought experiment, but nonetheless, the elevator example is a useful launching point for that type of inquiry. Yeah, the problem is that the equivalence principle is a local property that cannot really be expressed precisely in standard English. Clearly it will fail given a big enough lift to experiment in, since a big enough lift would essentially include whatever object is creating that gravitational pull, or enough to conclude its existence from other phenomena. However, these effects are non-local. You need two different points of reference for them to work, like your two baseballs. In fact, most tidal forces are almost by definition non-local. The precise definition involves describing curved spacetime and geodesics, but that one is really hard to visualize as a thought experiment. The thought experiment does offer insight though, as it is possible to imagine that, absent significant local variations in gravity, you cannot distinguish between free fall and a classical, inertial frame of reference without gravity. This insight provides the missing link that allows you to combine gravity with the laws of special relativity and therefore electromechanics, including the way light bends around heavy objects, which provided one of the first confirmations of this theory. Greater than you'd see them move closer because of tidal effects dictated by the fact that they're each falling towards the Earth's center of gravity, and therefore at, very slightly, different angles. This point isn't raised anywhere because it's mostly a pedantic point that has nothing to do with the thought experiment. You shouldn't try and decompose thought experiments literally, otherwise you'll get caught up in unimportant details like this. Just assume the elevator is close enough to the Earth such that the field lines are effectively parallel, or better yet, just pretend the elevator is in an infinite plate field. The assumption is the acceleration and the gravitation are in the same direction and the same magnitude. The point is that given these two, it's impossible to distinguish the two. If you think it's sneaky to implicitly assume they're in the same direction, I would point out that this is no different from assuming they have the same magnitude. It would be kinda dumb to say, well, this 1 meter per second squared acceleration can't possibly be equivalent to gravity because gravity is 9.8 meters per second squared, so the statement is obviously wrong and they're trying to trick me. Same thing for direction. To me, the layperson, the idea that you cannot distinguish whether you are in an accelerated frame or in a gravitational field seems wrong due to a very simple fact. The force that would be exerted from acceleration versus gravity is different. The force we think of as gravity comes from a center point that changes with your position, while acceleration comes from a uniform direction without regard to your position. I have two quite bright nieces. When I was explaining the equivalence principle to them, right away they saw that in the gravitational field of the Earth there would be tidal effects and in free space with just acceleration, none. I had to apologize and say that the explanation was oversimplified and really it would work, say, only for some creatures living exactly on the floor of the elevator. One of the two, at a challenging high school, made valedictorian, surprised to her parents who didn't know she had long been first in her class, then in college PBK, got her law degree at Harvard, started at Kravitz Swain, went for an MD, and now is practicing medicine. Bright niece. Sort of meta, but I always shudder when someone says that science has proven something. What sets science apart from most other methods of seeking answers is its focus on disproof. Your goal as a scientist is to devise experiments that can disprove a claim about the natural world. This misconception rears its head most prominently in discussions at the intersection between science and public policy. Climate change. How to handle a pandemic. Evolution. Abortion. But I've even talked to scientists themselves who from time to time get confused about what science can and can't do. The problem with believing that science proves things is that it blinds its adherents to new evidence, paving the way to better explanations. It also leads to the absurd conclusion that a scientific question can ever really be settled.
Hey guys, this is the Rogue YouTuber here. I recently had a big change in my life. I had a baby daughter. Here she is. If you could do me a favor and remember to hit the subscribe button and bang the bell, I'm hoping to really create a YouTube channel that really gets people excited and brings people the best, most interesting content collated from across the internet. I'm saving up to save my little girl to Carnegie Mellon Computer Science Department. So please remember to like and subscribe. See you next time.